warahmatullahi wabarakatuh. My name is Marania Nasura bintu Nizam and I will talk about introduction. Everyday living requires effective communication as it allows us to share information, express ideas, and develop meaningful social bonds. However, for individuals with speech or hearing impairments, sign language is their primary means of interaction. This presents a considerable challenge when they try to communicate with members of the general public who are entirely unfamiliar with these specific hand movements. Recent developments in computer vision and artificial intelligence have finally made it possible to build automated systems that recognize hand gestures and instantly translate them into text. By training intelligent models on diverse datasets, modern deep learning architectures can eliminate the need for costly or invasive wearable sensors by processing visual data directly from straightforward camera feeds. Therefore, this project focuses on utilizing cutting-edge object identification techniques to recognize American Sign Language alphabet motions, converting raw visual gesture into instantaneous textual outputs to promote a more inclusive environment. Next, I will talk about problem identification and motivation. The main obstacle for people who rely on the sign language is the general population's overall incapacity to comprehend their gestures. This creates a serious communication gap in crucial public areas, educational institutions, and commercial establishments. Currently, the absence of prompt on-site manual interpreters frequently results in miscommunication, frustrating delays, and a deep sense of social isolation when a person with a speech or hearing disability tries to access basic service. Manual interpretation has historically been the only practical option, but it is frequently unavailable, expensive, and completely ineffective for impromptu daily communication. This ongoing lack of smooth communication severely limits the independence of the deaf and hard of hearing group, preventing them from fully engaging in contemporary social activities. Because of these critical challenges, an automatic, dependable, and real-time system that can precisely recognize ASL alphabet hand gestures without human involvement is desperately needed. Next is the project objective. To successfully overcome these communication obstacles, our project is driven by three main goals. Our first objective is to develop a true American Sign Language alphabet hand gesture identification system that is based on a cutting-edge computer vision architecture. Our second objective is to create and evaluate a deep learning model with excellent accuracy that is tailored specifically for localized alphabet recognition. Finally, our third objective is to significantly improve communication accessibility by making sure that in a real-time setting, the system immediately displays the identified American Sign Language alphabet as readable text for the user. So this is our project scope. To guarantee technical viability and excellent performance throughout development, we have clearly defined the project scope across three core areas. First, the target vocabulary of the system is strictly limited to the 26 static hand motions that correspond to the latest A through Z in the American Sign Language alphabet. Second, the input medium relies entirely on standard real-time video feeds, which are obtained from a standard commercial camera or webcam for image capture and processing. Third, our algorithmic focus rests on the You Only Look Once or YOLO architectural family, which is trained on static picture dataset to serve as the foundation of our detection framework. The significance of our project is the effective implementation of the alphabet sign language detection system provides significant technological and societal benefits Socially, it empowers people with speech and hearing impairments by providing them with a dependable means of independent communication in important daily environments such as banks, clinics, and retail establishments. By translating hand signals into instantaneous text, it improves personal autonomy, confidence, and social integration while removing the ongoing reliance on manual interpreters or written notes. In terms of technology, this project served as a solid prototype showing how real-time object detection models can effectively address accessibility issues using inexpensive hardware such as common webcams instead of pricey wearable sensor globes. Ultimately, by demonstrating that low latency translation is possible on common processors, this work opens the door for more sophisticated assistive technologies in the future, including dynamic sentence processing and cross-platform mobile apps.
So next is our proposed solution is an automatic American Sign Language or ASL recognition system that uses the YOLO object detection algorithm to recognize hand gesture in real time. As shown in the workflow, the process begins with the user perform an ASL hand gesture in front of the camera. The camera system capture the image, then the YOLO model detect and classify the hand gesture into the corresponding ASL alphabets. Finally, the recognized letter is displayed to the user instantly. This solution provides fast and accurate recognition, support real-time detection, and help reduce communication barrier between deaf or hard of hearing individuals and people who do not understand sign language. This slide shows the overall system architecture of our real-time ASL recognition system using the YOLO 26 object detection model. The process begins with the user perform an American Sign Language hand gesture in front of the webcam. The webcam captures the live video and the system extracts individual image frame from the video stream for processing. Next, each frame is passed to the YOLO 26 detection model, object detection model. The model analyzes the hand gesture by extracting of features, detecting the object, and classifying it into the corresponding ASL alphabets. Finally, the predicted letter is displayed on the screen together with the confidence score in real time, allowing users to receive an instant recognition result. The lower section shows our model development process using RoboFlow, including image annotation, dataset preparation, model training, and evaluation. The model performance is measured using precision, recall, F1 score, and MAP A50 to evaluate its detection accuracy. This slide summarizes the algorithm and computational method and technical implementation used in our project. For the algorithm, we use YOLO 26, which is a real-time object detection model. It is selected because it can detect and recognize ASL hand gesture quickly and accurately while maintaining high efficiency for real-time application. For the computational method, the process starts with dataset preparation, followed by training the model using our annotated RoboFlow dataset. After training, the model is evaluated to measure its performance before being used for real-time prediction. For the technical implementation, the system is developed by using Python, which is YOLO 26 model for object detection, and RoboFlow for dataset management, annotation, and model training. This technology work together to provide an accurate and efficient ASL recognition system.
I will continue presenting our model design and development. First, as shown in Table 1, our system is developed using the RoboFlow platform, while the YOLO 26 small object detection model is used to recognize American Sign Language hand gestures. The system uses a webcam as the input device to capture live video, and the output includes a bounding box, the predict alphabet label, and a confidence score. Finally, the trained model is deployed through RoboFlow for a real-time testing. Next, Table 2 summarizes the dataset information used to train our model. The dataset consists of 1,354 images, representing 26 American Sign Language alphabet classes from A to Z. Each image is manually annotated using bounding boxes with the RoboFlow annotator. The dataset is then used for training, validation, and testing to ensure that the model learns to recognize different hand gestures accurately. Moving on to the target level section, the objective of our model is to recognize the 26 static American Sign Language alphabet gestures. During annotation, each hand gesture is enclosed within the bounding box and assigned the correct alphabet label. This enables the model to learn about the position of the hand and the corresponding alphabet simultaneously. Lastly, the operational workflow illustrates how the system works. The process begins when the user performs an ASL hand gesture in front of webcam. The webcam captures the live video, and each frame is processed by the YOLO26 object detection model. The model then detects the hand gestures, predicts the corresponding alphabet, and finally display the prediction together with the confidence score in real time. To evaluate our proposed system, we conduct a real-time testing using the RoboFlow deployment interface. During the testing process, users perform different American Sign Language alphabet gestures in front of webcam while training YOLO26 model continuously process each video frame. The system successfully detected the hand gestures, generate bounding boxes, predict the correct alphabet labels, and display confidence score in real time. Based on our observations, the model demonstrated stable detection performance under normal indoor lighting conditions with minimal latency. These results indicate that the proposed system is capable of providing accurate, reliable, real-time sign language. To further evaluate model's performance, we use 4 standard object detection metrics: precision, recall, F1 score, and mean average precision at 50% intersection over union, or MAP at 50. As shown in the table, the model achieved a precision of 98.5%, indicating that the most detected hand gestures were correctly classified, with every few false positive predictions. The recall of 97.7% shows that the system successfully recognized most of the actual hand gestures with only a small number of misdetection. In addition, the model obtained an F1 score of 98%, demonstrating a good balance between precision and recall, while the MAP at 50 of 99.7% indicates the excellent localization and classification performance. Overall, these results confirm that our proposed ASL recognition system provides highly accurate and reliable real-time recognition of alphabet gestures. The first screenshot shows the RoboFlow dataset dashboard, where all annotated images are managed. As mentioned earlier, our dataset consists of 1,355 images representing the 26 American Sign Language alphabet classes, with each image manually annotated using bounding boxes for model training. The second screenshot illustrates the system successfully detecting the SSL gesture A in real time. The model generates a bounding box around the hand, predicts the correct alphabet label, and displays the corresponding confidence score. Similarly, the third screenshot shows the successful detection of ASL gestures W, demonstrating that the training model is capable of recognizing different alphabet gestures accurately during live webcam testing. Finally, the training result metrics display the learning performance of the YOLO26 model throughout the training process. The graph shows that the training and validation lose gradually decrease, while the precision, recall, and MAP values improve consistently, indicating that the model learned effectively and achieved stable performance. Overall, these screenshots and graph further validate that our proposed system is capable of providing accurate and reliable real-time American Sign Language alphabet recognition.
So now, I will present the discussion of our project. So, our system achieved excellent performance with precision of 98.5%, recall of 97.7%, F-score of 98%, and MAP at 15 of 99.7%. This result show that the YOLO26 model can accurately recognize ASL alphabet gesture while providing a reliable real-time detection. So next, the strength of our system. So the main strength of our system is its fast real-time detection, simplified workflow using RoboFlow, and high accuracy. However, it is limited to static alphabet recognition, and performance may decrease under challenging environments or due to relatively small dataset. Next is comparison and findings. So, compared with traditional image classification, our system can both detect the hand location and recognize the alphabet simultaneously. So, this makes it more suitable for real-time application. And from our findings, we conclude that the YOLO26 model is effective for real-time ASL alphabet recognition. The combination of YOLO26 and RoboFlow provide an efficient development workflow while achieving excellent detection performance. Overall, this project demonstrates the potential of computer vision and artificial intelligence to improve communication accessibility for individuals with hearing or speech impairment. In conclusion, our project successfully achieved all of its objectives by developing a real-time ASL alphabet recognition system with high accuracy and reliable performance. For future work, we recommend expanding the dataset with more participants in different environmental conditions, developing the system to recognize complete words and continuous sign language synthesis, optimizing the model for mobile and embedded devices, and integrating speech synthesis to provide more practical communication assistance.
This is the model trained YOLO26 small object detection used in our project. After the model was trained and evaluated, it was deployed for a real-time testing using the webcam. For the real-time demonstration, the webcam acts as input device. It continuously captures live video frames, which are processed by the trained model for inference. For example, when I perform this ASL hand gesture, the model detects the hand and predicts the corresponding alphabet. As shown for the screen, the model recognizes the gesture of the letter B. The bounding box indicates the location of the detected hand gesture, and while the percentage represents the model confidence score. When the hand gesture is changed, the model processes the new incoming frame. The model processes the new incoming frame and updates the prediction accordingly. The predicted class is updated in real time based on the current hand gesture. Similarly, the system is able to recognize the trained ASL alphabet gesture. The output consists of three main components: the bounding box, the predicted SLL alphabet class, and the confidence score. The bounding box localizes the hand gesture, and the class label amplifies the recognition alphabet. And the confidence score indicates the model certainty and its prediction. Since the system processes continuous video stream, the detection is updated dynamically as the hand gesture change. This demonstrates real-time capability of the YOLO26 object detection model. Overall, this demonstration showed that the developed model can detect and recognize the ASL alphabet hand gesture in real time through a webcam. This system successfully provides the predicted alphabet bounding box and its confidence score as its output. This concludes the demonstration of our real-time ASL alphabet recognition system.